a grand total of 15 minutes, so we'll see how this goes. Alright guys, so welcome to quarter 4. So in quarter 4, we're going to be talking about electromagnetism. Basically, electrons. So remember October of last year in chemistry? Well, we're going to take the idea about electrons and we're going to stretch it out into physics over the space of 1 quarter. So electromagnetism starts with electrostatics, which literally means charges not moving, and it ends with magnetism, which is charges creating magnetic fields. There we go. Okay. You probably can't see it, but there's a cone of like purple fog, I guess, as the air around my my arc coil, my Tesla coil, is ionizing the air. So I have to give the lightning somewhere to go, and yeah, you would be good. Woo! Plumbing makes a really good ground because plumbing goes into the ground, and when something is grounded, it means you're basically allowing the charges to go somewhere. Well, electrostatics is what we get when charges are held in place. Okay? When charged particles or charged objects are held in place, we call that electrostatics. Electrons, static. Static means not moving. Okay? Static means not moving. So we're going to talk about electrostatics this week, and then next week we'll talk about current electricity, and then circuits, what happens when you force the current electricity to go where you want it to go. Then after circuits, we'll learn magnetism. Magnetism is what you get when you force the charges to create electric fields, and those electric fields create magnetic fields. And then that will basically be almost all of it. If we have a little time after that, we'll deal with quantum. And quantum is what happens when you force the electrons to move in and out of atoms at a very specific amount with a very specific amount of energy. Cool? Okay. So like I said, that's my son Lucas. He was at the time 2.5. Now he is 3, and he's just as cute. This is him at the top of the slide. This is him with the hair up. So why does his hair go up? Why does the hair go up when you go down the slide? Everybody knows static electricity, right? This is why when you get out of your car, it's like zap. If you want to keep the car from zapping you, just hold on to something metal as you get out of your car, or turn the back of your hand and touch the back of your hand against something metal, because you don't have as many nerve endings on the back of your hand as you do your fingertips. If you like zap the back of your hand, you're going to be okay. But you like static electricity, right? This is why if you take a comb and rub it in your hair, you can pick up little pieces of paper. It's also why Pikachu can electrocute things. I will electrocute you. Oh, and this video is not running, which is too bad. Let's see if I can make it run. Otherwise, I'll have to just describe to you what happens. So it happens that almost all gas stations, a couple times a year, that someone will create a fire. Yeah, it's not going to work. Someone will basically create a fire by just walking up to their gas station and or walking up to the gas pump and touching the pump. So a lot of pumps are grounded. They try to take this into account. But what happens is you pump your gas, then you get back in your car and you sit down with the door open. Then you get out of your car, and where you would normally zap yourself on the car door, you zap the pump, and the vapors around the gasoline burn. Great fun. There's tons of YouTubes about it. Again, it happens to almost all gas stations once or twice a year, just because people, and it's almost always women. Now, and no one knows why. Science psychologists are working on this. There's a Nobel Prize in this. For some reason, when women pump gas, they like to pump the gas and then sit down in their car and look at the car. When guys pump gas, we want to make sure everything's working properly. We pump the gas, we stand next to it and watch it. We just want to make sure everything's going properly. Women are like, the gas will end up in the car, I'm going to sit down. No one knows why they do that, but that's what they do. So next time we pump gas, we'll look around. The men will be standing at the pump going, and the women will be sitting down in their car on the phone. Okay, electrostatics. Electrostatics is what you get when charges create fields around them. So electric charges held in place will create an electric field around them. much like masses, will create mass fields. Okay? In fact, there's a huge number of analogs between what we learned about masses and universal gravity and what we're learning about charges and electric fields. So what keeps the moon from flying away? What keeps it spinning around the Earth?
Gravity.
Gravity. And when you say gravity, what do you mean? What specifically about gravity makes that happen? Why? Why is it being pulled? Where does the gravity come from? What is the mechanism? The mass, exactly. So the mass of the Earth creates a mass field, a gravitational mass field around the Earth. The moon, because it has mass, responds to that mass field. Any two objects with mass will be attracted to each other. Okay? That's why Benson and Lane, because Benson has mass and Lane has mass, they're attracted to each other. But not as strongly as Bowen and Lane, because Bowen and Lane are closer together, so they have a greater force of attraction. Make sense? Okay. So just a reminder, that's how it works. Well, fields are the same thing. Just like the Earth that has mass creates a gravitational field, charged particles create an electric field. And when you put a charged particle into another charged particle's field, they will feel an attractive or repulsive force. Okay? Any charged thing creates a field around it. If you put another charged thing in that field, that charged thing will either be repelled or attracted to the center of that field. Repelled from or attracted to the center of that field, whatever's making that field. How do you know if it's going to be repelled or attracted?
Charge.
What about the charge?
If they're opposite, they're not opposite. Yeah.
Exactly. If you put a positive test charge in a negative field, it's going to be attracted to the center of that field. If you put a positive test charge in a positive field, it's going to be repelled from the center of that field. Question or comment?
What prevents the moon from just like going into the Earth?
It's fast. Yeah. The question was, what prevents the moon from crashing into the Earth? It's fast. It's constantly moving. So it has momentum, and that momentum is like the ball on the end of a tether ball. So if eventually if a tether ball loses its momentum, it will fall and hit the pole. Just like if the moon suddenly, if God took the moon and went slow down, it would go. That's why you should live good lives. Otherwise, God might drop the moon on you. Okay, so we remember from fourth grade that there are protons in the nucleus and there are electrons zooming around the nucleus. So the electrons are zooming around in clouds. We learned all about this in chemistry, how they're oriented in orbitals. What's important for us is what those electrons are doing. Protons in materials do not move. Electrons can move. Because electrons just naturally move. They like to move from atom to atom to atom to atom. The protons do not move. Electrons do. Conductors are materials that allow the electrons to travel through the material. Insulators are materials that only allow charges to move on their outside. One of those things that you have to unlearn. You were taught in elementary and middle school that insulator means no charge movement. Using insulator, you don't need charge to move. And conductors mean charges to move. Well, that's not entirely the case. You know this implicitly because if you take a balloon and rub it on your head, it'll stick. Balloons rubbed on heads pick up charges. In fact, I have a balloon. We'll test it over here with Angelina's hair.
Angelina's like, that's great, just what I wanted. I would totally be happy to see. Why don't you want to hear that?
You can try my hair too.
Let's wear Benson's hair.
It wouldn't work.
That wouldn't.
Yeah.
Whoa!
Because you saw I was gonna have one.
I see there was a balloons.
Yeah, exactly.
It's gone.
So that's where he gets it. Anyway, yeah. So let's see if we can stick to anything.
Your hair's long.
Yeah, it's gonna get cut on Friday. Oh well, it doesn't want to stick. It'll just stick to me.
Stop.
So, the crazy thing about rubber is rubber likes to take electrons. Rubber's molecular structure is such that there's a lot of places for electrons to stick, which is why your shoes on floors, why the vinyl in your car, vinyl's the same kind of thing, vinyl and rubber have a lot in common. The static electricity is coming from the vinyl seats and the vinyl dashboard. Rubber is really good at picking up charges. Hair, on the other hand, is really good at giving up charges, which is why it's really fun to rub balloons on hair. So, what's happening when I rub the balloon on the hair? What's happening to the electrons? Yeah, they're leaving the hair and they're going to the balloon. So the balloon is picking up what kind of charge? Negative. And the hair is getting what kind of charge? Positive. Hence the attraction. Let's stick up there. Stay up there. No. Okay. Well, anyway. Okay, you've had your fun. There we go. If you want to try it, here's a balloon. It's already been a little bit charged up. Okay, so the thing to remember, guys, is this. This is extremely important. Are you ready? Protons do not move. Okay? Protons are fixed in the material. They do not move. Electrons move. Now, why am I telling you something so obvious? Because of convention. Convention is 30 stormtroopers shooting at the hero will not hit the hero. Okay? Here's the convention. If you have a circuit, this is a circuit with a battery. If you have a circuit, charges move from the positive to the negative in this direction. They move in this direction. Are you ready? Are you paying attention? Electrons are negatively charged. They can move. When we do circuits, in a few weeks, it is conventional current that moves. Conventional current is positive. I know. It's just the way it has to work. It has to work this way so the math can be, so the students can be taught. Kind of like how you learned in second grade, 4 divided by 3 is 1 remainder 1. You have to learn that conventional current is positive, and positives move away from the positive pole towards the negative pole. Positive moves away from the positive pole to the negative pole. Conventional current is positive, but protons don't move. Okay? It's critical you understand this. Okay? Are we cool? Okay. So what moves? Electrons. But in diagrams, it is conventional current that moves in the opposite direction of the electrons. Okay. So now we're happy. Okay, moving on. Any questions?
We're going to relearn that, right?
Yes.
Okay. No.
We totally will. No, we totally will. Over and over again. Okay, so a couple ways to charge materials. The first way is the balloon on the face, and that is charging by contact. When you charge by contact, you can take a charged object and rub it or touch it to a non-charged object or an obsolete charged object. Anyway, the charges will flow. Charging by contact is just charging, you touch it, the charge flows. One of these days, let me get around to fixing this thing. Problem is, there's a wire, and I'm afraid if I pull it, the wire will come out.
How did tasers work?
Like police tasers? Good question. There's a capacitor that is charged up, and the capacitor stores charge, and I'll tell you what a capacitor is in the next unit. A capacitor is like a super battery, whereas a battery allows large quantities of charge to go over long amounts of time. A capacitor allows very small amount of charge to be released all at once. So there's a capacitor, and then either through gas or through springs, depending on the model, it'll either fire two prongs, either with a gas jet or through springs, and those two prongs go woo, and they'll stick to you. And then once it connects, basically once your body connects to circuit, the capacitor will discharge, and it'll discharge the electricity through you, back to the capacitor, through you, back to the capacitor, through you, back to the capacitor, and hopefully it's enough to cause your muscles to go spasm that you follow. That's how it works. So.
What about the ones that have to be
It might not.
Those basically work just like this. Instead of having two little wires, the prongs have wires on them, little thin wires. So instead of having those little wires, it basically just takes care of the wires and just has a capacitor that releases electricity like this. So the handheld taser like you can buy is like this. So only it has both poles built in, one on one side, one on the other. It just takes a capacitor, discharges it.
How bad does it hurt? A lot.
You want to tell
Not a lot.
Come up here, we'll find out.
Again, one of these days I'm going to fix this, but I'm afraid I'm going to break it by trying to fix it. It works some of the time. Okay, so that's charging by conduction, charging by contact. The really cool one is charging by induction. Induction does not require any contact. Question?
What happens when you stick a fork in a toaster?
When you stick a fork in the toaster? Depends on what the fork touches. So if the fork touches both sides, then the electricity will not go through the heating elements, it'll go through the fork instead. And it'll turn the fork into a heating element. So what's happening is those heating elements have a huge amount of resistance, so you're basically trying to force a lot of electricity through a very small pipe that makes the pipe heat up, kind of like old style light bulbs with a little filament. So basically that's what a toaster is, it's a bunch of little light bulbs. But if you stick a fork in there, you bridge, then you short out the heating element and you turn the fork into a heating element instead. Okay, this is how charging by conduction works. It's really cool. You take a charged object and you bring it towards, but not touching, something that can be charge separated. So you take your charged object and you bring it near an object that can be what's called polarized. So polarized means the charge can be separated. So there's the separated charge. It's kind of like if Taylor Swift walked into that door, all of the guys would be like, Taylor Swift, they're all going to move over here. I want to sit on this side of the room. Okay, and all the girls would be like, I'll sit on that side of the room. And then John Cena walks in over here, he's like, hello ladies, and all the girls are like, I want to sit on this side of the room. That's what's happening. So this is the Taylor Swift, and these are the guys right here, and these are the girls over here. Make sense?
I would say right.
Yeah, you can probably just stay there and like, yeah, whatever. I'm making this stuff up as I'm going here. But then, once you've got the charge separation, you do what's called a partial ground. Okay? Once you've got a charge separation called a polarization, you do a partial ground, where basically you create a place for the charges to go. That's the symbol for a ground. Big line, littler line, littler line. Which charges are going to flow? In this diagram, which ones are going to flow? Will the positives flow or the negatives flow? Positives. Okay. Yeah, because the positives are repelled from the charged object. So there's a charged object, you are repelling the positives just leave. The girls are like, we're just going to go. Bell rings, they go, guys stay. I'm working with what I got here. Yeah. Okay, so that's how charging by induction works. You bring a charged object near an object that can be polarized. The object gets polarized, then you do what's called a partial grounding, and you allow those repelled charges to flow. Now, once those repelled charges flow, if you took the charged object away, what charge would this thing be left with? Negative, because you're allowing the positives to flow. You bring a positive charged object, positives are repelled, negatives are attracted, you do a partial grounding, the positives leave, and the charged object becomes, or the neutral object becomes a charged object that is negative. Does this make sense? Okay. Still madly scribbling. There's one more point, but most important concept in all of physical science: opposites attract, likes repel. For some reason, works in dating too. Okay, give me a thumbs up if this concept makes sense to you. Some people just pick it up right away. Some people are like, I don't understand. Okay. Now the opposite would also be the case if you brought a negatively charged object towards a neutral object. What things would be attracted? If you brought a negatively charged object to a neutral object, what would be attracted to the negatively charged object?
Positive.
Positives. And what would be repelled?
Negative.
Negatives. Okay, cool. Okay, so here's a bunch of animations about charging by induction. You probably don't need them, but I'm going to walk you through them anyway because they're really cool, especially like this one here. So let this one restart. This is how you're going to be charging by induction with electroscopes. The electroscopes are right back there. If you look straight back, they're in little Erlenmeyer flasks. They have a little metal ball on top. And then just to the left of that is the Van de Graaff generator. So those two big metal boxes on top, those are oscilloscopes. Below those are electroscopes. So this is what you do. You bring a charged object to a neutral object. In this case, the charged object is negative. Positives are attracted to negative. You partially ground the negatives. So now when you remove the charged object, the remaining object stays positive. You're going to be doing this in the electroscope lab, which is Thursday. So similarly, this is a diagram from your textbook. You bring a negatively charged rod to a neutral object. The positives polarize, positives towards the negatives, negatives away from the negatives. Then you partially ground those negatives, negatives leave. When you bring the object away, the object is left positive. Okay, shall we move on? All right, cool. Charging by friction. So this is what we did with the balloon and my hair. And again, there's Lucas, and he knows all about charging by friction. He'll tell you all about it. Happens every time he goes down the slide. So some things like to gain electrons because there's holes in their molecular structure where the electrons can hang out. Some things like to give up electrons because they don't hold onto their electrons very well. So rubber loves to gain electrons. Plastics love to gain electrons. Most of the inside of your car is plastic. From the dashboard to the seats, it's all organic compounds. Organic compounds love to give up gain electrons. Rubber and plastics love to gain electrons. Glass loves to lose it. Fur and hair loves to lose it. Leather loves to lose it. So if you wear a leather jacket in a car, you're going to build up a lot of charge because the leather wants to lose electrons, and the organic compounds, the nylon and the vinyl that make up your car seat, your dashboard, and your steering wheel, they want to gain electrons. And skin also likes to lose electrons. So if you really want to get a shock, try it naked. Oh, show. Oh, it's like I know all about it. Okay, so how are we doing so far? Good? All right. There's this 300-year-old piece of technology which we still use called an electroscope. The electroscope basically has three pieces. It has a metal knob connected to a metal rod and leaves at the bottom. And here's the cool thing about the leaves. They're both connected to the metal rod and they're both made out of metal. So if you bring a negatively charged rod towards the knob, positives go up, and what happens to the negatives? Negatives go down, which means since both of those leaves are negative, what are they going to do? They're going to repel. No, they're just going to repel. Yeah, they're just going to go boop. So hopefully they repel. Sometimes you build the charge up so much they just go flying off the little hook they're on. But that's how the electroscope works. If you bring a negatively charged rod to the top of the knob, positives go up, negatives come down, and the leaves will separate. Now, if your electroscope is neutral, the exact same thing will appear to happen with a positive rod. If you bring a positive rod, negatives go up, positives go down. Okay? So basically, the electroscope is really good for determining if whatever you're waving over it is electrically charged. Yeah?
So if you charged it negative and then you did it with a positive, they would go.
Yes, and that's the next step. So what you're going to do is you're going to bring the negative rod to the electroscope, and then you're going to touch it, and the whole thing will become negative. So if the whole thing becomes negative, and then you bring a positive rod, are you paying attention? If the whole thing is negative and the leaves are out, if you bring a positive rod to the electroscope, the negatives will go up and the leaves will go in because they'll lose some of their negative charge. Make sense? Okay. Anyway, it's a really, some of you are going to have a really great electroscope that works great. Some of you are like, it's not working! It's because you've got too much electricity in the air. But we'll play with those on Thursday.